we will be learning about stoichiometry. Now, it may seem like a complicated word, but really all it means is the relationship between the compounds in a substance taking place in some sort of reaction. And yeah, this also sounds complicated, but I'll walk you through it. Now, to understand stoichiometry, first we'll have to understand the mole. The mole is an SI unit for amount of substance, and it can be applied to any object. Essentially, it's Avogadro's number, which is around 6.022 times 10 to the 23rd, and it was named after this guy, Avogadro. And this also ties into molar mass, which is the mass of a sample of a compound divided by the amount of substance in that sample, essentially grams per mole. And here is a equation that can help you with that. Another important concept to understand is atomic mass. It's the mass of an atom, and it's approximately the number of protons and neutrons. And you can see the atomic weight, which is distinct but similar, on the squares of the periodic table. And this also ties into molecular mass, which is the combined atomic masses of the atoms. This is measured, as well as the previous one, in AMU, atomic mass units. They're also known as the Daltons. And the molar mass of a compound is conveniently equal to its molecular mass, which is pretty important. You might want to memorize this. So x grams per mole is equal to x AMU. And so because of this property, in the context of equations, we can use molar mass to go between x AMU and x grams. Now, let's take a look at this example. Carbon dioxide. Its molecular mass would be the sum of all of its constituents. So if we add up these, we get approximately 44 atomic mass units. Now, we can't determine the moles in carbon dioxide until we are given the mass of the substance. Recall that it's essentially the number of atoms in a substance divided by Avogadro's number. So we can't actually figure that out yet. And the molar mass, I've presented this, we can't actually get that until we have the moles in carbon dioxide, which is, as we previously stated, we can't get it. So now let's take a look at stoichiometry, now that we've looked at all of the terms and important things to know. So let's take a look at the sample equation. Now, before we can apply these methods of stoichiometry, we'll have to kind of simplify the reaction. Now, this is pretty simple. You could probably do it if you didn't do it before. And it's just based off of the concept that conservation of mass. You can't have deleted or added mass, if that makes sense. Essentially, there's one carbon on this side, so there should be another on the other side. So let's get into this. Let's assume that there's one carbon for now, and check that works. But we've run into a problem. There are 4 hydrogens on one side and 2 on the other side. But for now, let's just keep it as 1, since we don't know what's going to happen. Now let's move to the oxygens, and we run into another problem. There's 2 of the oxygens on one side, and there's 3 on the other. So what we can do is essentially keep the methane and the carbon dioxide with the coefficient of 1. Oh, and by the way, this is the combustion reaction for methane. I decided to use this as a base example. But yeah, we can keep the coefficient of this oxygen as 2, while also keeping the coefficient of this as 2 as well. That way we can end up with 4 in total. And after we do that, our demand for hydrogen is satisfied since we have 2 on both sides. So let's just go back and check that we have 1 of each or 2 of each on either side. The carbon numbers match, the hydrogen numbers also match, and the oxygen numbers also match. So now let's get into what we're here for, stoichiometry. So we have this equation, and we need some kind of given, we need to know the number of grams. So given 48 grams of methane, how many grams of oxygen do we need? is the problem we are presented with. Now, to do that, first we'll have to see how much AMU is in the methane. We only have one molecule of methane and one atom of carbon, so we can just plug those in. However, we have 4 atoms of hydrogen, so we're going to have to multiply that by 4. And so we end up with 16 as our atomic mass. And if you recall previously, we can use the equation for molar mass in order to take those 48 grams from the given and divide that by the 16 atomic mass units we have to get 3 moles. Now we should take those 3 moles and notice how there's a coefficient of 1 on this methane and there's a coefficient of 2 on this oxygen. This tells us that for every 1 methane molecule, we're going to need 2 oxygen molecules. It doesn't matter if there's more atoms in 1 molecule, because stoichiometry is all about ratios. Keep that in mind. So now we have those 3 moles. So we know that we need 6 moles of oxygen to complete this reaction. And we're only going to be looking at the reactants, since these don't matter as much. And if we look at these like boxes, we can see that 1 oxygen molecule is around 16 AMU. It's okay to round because there's no need to, So after that, we can do the same conversion and find that 1 mole of oxygen is 16 grams. And this makes everything else relatively easy. All we need to do now is find how much 1 mole of oxygen is in terms of grams. And since we found that, we can do some simple multiplication and find that 6 moles of oxygen are indeed 96 grams. Now, this was a fairly basic chemistry lesson, and you might find that 48 grams and 96 grams seem pretty like the same. And this is just a coincidence, since methane's atomic mass was found to be the same as oxygen's, and the coefficients were different. But yeah, I assure you, this is just a coincidence. Now, because this is just the very basics of chemistry, and you'll need this for later on. There's other stuff to learn, like what kind of bonds there are, and what specifically dictates how reactions form. But for now, these are the very basics. Thank you for listening.